Welcome to the Creative Commons RX podcast. Before diving into this episode, I want to ensure we're all on the same page. This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.
You know, when you think about medicine, you probably picture a small, simple pill, right? Something easy to swallow, easy to understand. But there's a quiet revolution happening right now, and it is powered by absolute giants. Let me show you what I mean. Okay, so on the left, you've got a drug we all know and love, aspirin. It's a tiny, elegant little molecule weighing in at about 180 daltons. But on the right, that's a biologic drug called infliximab. It's used for things like autoimmune diseases, and it is a massive, sprawling protein with a weight of almost 150,000 daltons. And to put that in perspective, infliximab isn't just a little bigger. No, it's over 800 times larger than aspirin. That is literally like comparing a bicycle to a jumbo jet. This unbelievable difference in scale is the core challenge we're facing, and it's why medicine is getting so much more complex and so much more powerful. What we're talking about here is a whole new class of drugs called biopharmaceuticals, or as most people call them, biologics. And these are by far the fastest growing class of new drugs on the market. They represent a huge shift. We're moving away from simple chemistry and diving headfirst into the world of complex biology. So what is a biologic, really? Well, think of it this way. Instead of being built in a chemical lab, these drugs are grown or derived from living sources, like cells. The main players are enormous proteins, things like antibodies, and something even more fundamental, nucleic acids, which are the very building blocks of groundbreaking gene therapies. But here's the thing. Being a giant comes with some giant problems. The very size and complexity that makes these drugs so incredibly effective also makes them unbelievably fragile. So the big question becomes, how in the world do you get these delicate giants to work inside the beautiful chaos of the human body? So why are they so fragile? Well, it all comes down to shape. A protein drug's power comes from its precise three-dimensional structure. It's like a super intricate piece of origami. From the basic chain of amino acids, all the way up to how the final pieces fit together, every single fold has to be absolutely perfect. If even one tiny part of that delicate structure unravels, the drug is completely useless. Think of it like a lock and a key. Insulin is the perfect example. Its very specific 3D shape is the key that fits perfectly into the lock on our cells, telling them to absorb sugar. If that key gets bent or broken, it's game over. It cannot unlock the cell. And this is exactly why you can't just swallow a protein drug like insulin. The second it hits the acid in your stomach, it starts to unfold, losing that critical shape. Then digestive enzymes swarm in and just chop it to pieces. Your body treats it like food, not medicine, completely destroying the key before it can ever find its lock. So if the body is such a hostile environment for these giant molecules, how do we protect them? Well, this exact problem has led to an explosion of some truly ingenious science, all focused on one single goal: building smarter delivery systems to shield this precious cargo. Scientists have come up with some incredibly clever packaging. One method, called pegylation, is basically like attaching a molecular shield to the drug. It helps it hide from the body's immune system so it can stick around longer. Another approach uses liposomes, these tiny bubbles of fat that essentially wrap the drug in an armored car, protecting it on its journey through the body. But just protecting the drug isn't always enough. I mean, what if the delivery vehicle itself was a smart bomb, a homing device that could actively seek out its target? Well, that's the incredible idea behind a technology called antibody-drug conjugates, or ADCs. Take a look at this molecule here. This is DM1, an incredibly powerful chemotherapy drug. You can think of it as the warhead for our smart bomb. It is way too toxic to just inject into a person by itself. But what if we could attach it to a guided missile? And that's where the antibody comes in. It's the massive homing device. But as you can see from this chart, there's a pretty wild catch. The antibody carrier makes up over 98% of the drug's total weight. The actual medicine, the payload, is just a tiny 2%. It's kind of like sending a massive cargo ship just to deliver a single tiny but crucial package. As amazing as that is, the next frontier goes even deeper. Instead of just delivering a drug to fix a broken protein, what if we could hack the body's own source code to stop it from making that broken protein in the first place? Well, welcome to the world of nucleic acid drugs. Okay, so this new frontier has three main strategies. First up, gene therapy. This is like uploading a new, correct file to your cells so they can make a protein they're missing. Then you've got antisense drugs, which act like a patch over a typo in the genetic code, helping the cell read the instructions correctly. And finally, there's RNA interference, or RNAi. This one is super clever. It actually hijacks the cell's own defense systems to find and destroy faulty genetic messages before they can do any harm. So with all these incredibly precise, super targeted therapies, you might be thinking, are the old rules of pharmacology, the ones designed for simple little pills, are they just obsolete now? Well, the answer, maybe surprisingly, is no. Not at all. These new drugs don't erase the old rules. They just create new, much more complex ones. They create a ripple effect across our entire understanding of how drugs work in the body. And here's the fascinating twist. While that giant biologic molecule gets cleared from the body in a totally new way, that tiny toxic payload it carries is still a small chemical, and that means it has to be processed by the body's old-school detoxification system, those liver enzymes we call CYPs. So even with these futuristic drugs, we still have to play by the old rules to avoid dangerous side effects. This complexity changes everything, even how we make cheaper versions of drugs. For a simple pill, a generic is an exact chemical copy. It's like photocopying a document. But for a massive, complex biologic, making a perfect copy is basically impossible. It's more like asking two master chefs to bake the exact same incredibly complicated cake. So instead, we have biosimilars. They aren't identical, but they're proven to be so similar that they get the exact same result. The science here is truly breathtaking. These magic bullets are getting smarter, more targeted, and more powerful every single year. They are completely changing how we treat disease. But all this progress forces us to ask a final, critical question. As we create these incredibly sophisticated therapies, how do we make sure they become real solutions for everyone and not just for a privileged few?
This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.